Well, let's go over the right answers to the review questions on ionic and covalent bonds. So you should have already answered all these questions and already submitted them to me if you're online. Question number 1, when most atoms combine to form molecules using covalent bonds, how many valence electrons are needed to make the bond? Okay. So most all the elements in the periodic table, they need 8 is what they need. With an exception, there's one element that's an exception to this, and that was hydrogen. Hydrogen only needs 2. Everything else, they're always trying to get 8 electrons in order to make that bond back and forth. Second question, what's the name of the covalent bond that shares? First one says 2 electrons, that's a single covalent bond. It's one pair of electrons or 2 electrons. Second one, letter B, 4 electrons. That's 2 pairs, so that's a double covalent bond. 6 electrons, that's 3 pairs, so that's a triple covalent bond. Now, I'll also give you an advice on that. I might ask it as number of electrons, 2, 4, or 6, or I might ask it as pairs, 1 pair, 2 pair, 3 pair. So make sure that you read the question as to what's being asked. Okay. Question number 3, describe what's taking place in a coordinate covalent bond. Now remember, in a coordinate covalent bond, normally in most covalent bonds, 1 electron comes from here and 1 electron comes from this element, and they share those electrons back and forth. Right, so an electron came from each of the 2 elements. But in the case of the coordinate covalent bond, this guy over here doesn't have enough electrons to give up. But this one right here does, so he gives both of the electrons to the bond. Right, so both electrons come from one element in the bond instead of one from each element. Question number 4. Why do molecules like carbon dioxide have a linear molecular geometry, but other molecules with 3 elements also they have a different molecular geometry? Well, in this one we'll draw them. So if we do carbon dioxide, he's got 4. And then we got oxygen, they got 6. There's his 6. Here's the other oxygen, he's got 6. So if I do my circles, to help me visualize how many they got. If we look at the carbon in the middle, he's got 1, 2, 3, 4, 5, 6. And this oxygen over here has got 1, 2, 3, 4, 5, 6, 7. All right, well, let's use one of these and one of these. That now makes it so this oxygen's got 2, 4, 6, 8. Sweet, he's happy. This oxygen over here, he's got 1, 2, 3, 4, 5, 6, 7. Well, let's put this over here and bring this guy down here. And now he's got 8. And what about the carbon in the middle? 2, 4, 6, 8. So he's happy. All right. Now notice in this case, the electrons are on the carbon. They're all bonding on opposite sides. Okay. Now if we do a different one, if we do water, so here's water. He's got 6, 3, 4, 5, 6, and then we're going to put hydrogen on this side and a hydrogen on this side. Okay. So now if I do my circles, this hydrogen's got 2, this hydrogen's got 2, and the oxygen in the center, he's got 8. So he's all happy. And now it would seem like, well, these 2 electrons here should keep those hydrogens sitting there so that they'd stay straight, but they don't. Instead, these guys kind of bump up towards the top, and they like to be near each other, but not next to each other. So instead, we're going to get this. And then we end up with a hydrogen here and a hydrogen here. So we end up with this bent shape to the molecule. It ends up like this. And why? It's all because of these 2 unbonded pairs of electrons. The electrons that are not being shared, those actually take the hydrogens and push them down, so we end up with a bent shape. Now going back to the carbon dioxide, notice he does not have any non-bonded pairs of electrons, so all of a sudden they go and they hold straight across. Okay? So that's why some have linear shapes and some have bent shapes and even other different shapes that we talked about in those other notes with all the balloons. All right, number 5, draw the electron dot structure for the following compounds. And you use X, O's, and E's to represent the electrons around each one. So let's get rid of these. All right, first one we got HBr. So Br's got 7. There's his 7. Okay. He's got 1 spot over here that's missing 1. So we're going to put the hydrogen there. Right. And if we do that, notice now there is 2 for that hydrogen and there's 8 for that bromine. So he's happy like that. Right. We could also write it this way. where that single bar indicates these two electrons that are being shared. And then we could add bars to indicate those non-bonded pairs of electrons around the outside. All right, we go to I2. Iodine, he's got 7. There's his 7. Then we put another iodine down here. He's got 7. So here is his 8, and there's his 8. So that's the structure for I2, the diatomic molecule I2. And it's just a single covalent bond between them. All right, erase these, and we'll do the next ones. And is it 5? All right, OH with the -1. So if I have the oxygen, he's got 6. And then we have a hydrogen. Well, the hydrogen can go here. That makes him happy. And the hydrogen we can't do a double bond with a hydrogen. Why? Because he doesn't have another electron to supply to this. Now if I do this other oxygen up here, notice he's got 1, 2, 3, 4, 5, 6, 7. He's short one. But this is a -1 polyatomic ion. What does it mean to be negatively 1 charged? That means he's got an extra negatively charged electron. And what ends up happening is we have an extra electron that's put in there that came from some other atom somewhere else. And now it's negatively charged, so it can bond to something ionically. Okay? And we represent that as a little electron. All right, sulfur dioxide. This one does have a coordinate covalent bond. So we got sulfur, he's got 6, 4, 5, 6. And we got an oxygen down here, he's got 6. All right, so if I circle this guy, that gives him 7. Circle this guy, that gives him 7. So we're going to bring this down, we're going to bring this up. And that makes that sulfur and that oxygen happy, right? They both have 8. But we're still got to get another oxygen. So we're going to put the other oxygen up here. And what he has is he will supply those 2 electrons to this. All right, so that we end up, oh shoot, I did that backwards, didn't I? I'm looking at my notes all of a sudden, I'm like, well, that's not right. Hold on. So what ends up happening, I'm sorry, the sulfur, he's got the electrons, he's going to supply them to that oxygen. Otherwise, that oxygen was giving them up and it wasn't going to work out right. So he gives up 2 electrons to that oxygen, all right? And that's a coordinate covalent bond. And by doing that, what we end up with is, I'm going to bring these guys up, and we get these here. Now I've got 8 around that oxygen, I got 8 around the sulfur, and I got 8 around this oxygen. Right? That sulfur is supplying both of those electrons. Now, is that the only direction that this could go? If this is oxygen 1 and this is oxygen 2, couldn't I end up with this also? Where this is oxygen 2 and oxygen 1, so that now my coordinate covalent bond is on the bottom? Yep, I could. And that's called resonance, where it goes from here to there, right? And it alternates back and forth in those 2 different types of forms. All right, one more. We got NP. So we got nitrogen, he's got 5. And we got phosphorus, he's also got 5. We gotta have at least a single covalent bond. Make my circle, there's 6, and there's 6. So let's bring this in, bring that in. That makes 7 for both of them. Now let's bring this down and bring this down. And that makes it so they both have 8. So what do we have? We have a 1, 2, 3. We have a triple covalent bond between the nitrogen and the phosphorus. All right, define the following. What's an electron dot structure? Well, that's what we've been doing back here. Where what you do is you put the symbol down and then you represent its valence electrons with some sort of symbol. We use circles and X's. Some people use E's, some people use dots, right? I like to use circles and X's so you can see which ones that these are the nitrogens and these are the phosphoruses. That's why I use circles and X's. So commonly they just use dots, but all right. Second one, metallic bond. Metallic bond, remember from the notes, is that you have all these copper atoms. So here's a copper, here's a copper, here's a copper, 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 copper. Each one of those are copper atoms, and then what you have is you have the valence electrons that are in between that are flowing back and forth. And that's what's holding all of those atoms of copper together to make a copper wire. That's what's holding my ring together, is that we have atoms of titanium, and then I have valence electrons that are floating in between that are holding my ring together. So it doesn't all of a sudden go and just fall apart. It's the valence electrons floating in between that keeps it together. An ionic bond. An ionic bond means you have a positive and a negative that are attracted together. So one of them gave up electrons, the other made him negatively charged. Because the one lost electrons, he has a positive charge, and we end up with this attraction because of that opposite charge. Really, really, really strong bond. They tend to be solids at room temperatures. Ones that are covalent tend to be gases and liquids at room temperature because it's not as strong of a bond. Valence electrons. Valence electrons, those electrons in the outermost ring. If we were to go back and draw electron configurations that looked like this, right, from way back earlier in the year, and we put electrons in 2, 2, 6, 2, right, it's those ones that are in that outermost ring, those are the valence electrons. And that's what we keep drawing in here, is we're just looking at the valence electrons for these. Octet rule. The octet rule, remember when I'm making these little circles, which is just a little help to visualize it. You don't have to have the circles drawn. Again, it's just a way of helping you see that we're following the octet rule. Octet rule is that this phosphorus now has 8. This circle, the nitrogen, has 8. That's the octet rule. Because they want to have 8 electrons in their outermost ring. And they'll either share electrons, or they'll do the coordinate covalent bond idea over here to get 8 electrons. They'll do something to get it so that they can get up to 8 if they possibly can. All right. Coordination number. Coordination number was when we did the sodium chloride. And remember we said that sodium chloride is really not Na and Cl, where this is positive and this is negative. I know that's what I taught you, but really it's a little bit different now as we go deeper into chemistry. Really, we got the sodium's got chlorine here, and a chlorine here, one in front, one behind. And then the chlorine has a sodium here, and a sodium here, and a sodium here, and one in front, one behind. All right. But that coordination number is that the sodium actually has 1, 2, 3, 4, 5, 6 chlorines around it. All right, so it's how many negative charges around that positive. That's what gives us a coordination number. All right, I'm going to stop there. We're going to go to part number 2 before I run out of time. So, see you in a bit.